Yeah, we're there.
That's good.
Okay.
So the suggestions are very excellent. So I put a new email also and check whether that style is okay. Maybe
Yeah,
Christopher
great.
can, yeah, Christopher can come up with a form or template or something
Oh yeah, I
for
like that better. Yeah.
two different things. He said, uh, Emmanuel saying send two different emails. One of them will be about the text, the actual text with link and everything when it's happening. The other one is about the speaker, information about the speaker. So, I send out that one.
Do we need two different emails? Why is that?
I don't
Would you
know.
not?
I mean, he was suggesting maybe we can put together. I don't know. I mean, that's
So
something we can debate.
one email has the information about the speaker, and what does the other email have?
The normal, our text meeting with the link and everything, with a link.
But sure, yeah, wouldn't you want to like join the two? In the case like if there's a speaker who's coming, then you'd want to put the link for that show in the same email.
Yeah, we can do that. I mean, you can come up with something because you are an IT person. You will know.
Well, I mean, just like, yeah, so that's how we normally do it. Someone is presenting something, we'd have the name, the title, what they're presenting, and then the link all in one email. So people.
Okay, that's fine. That sounds good. So if you can, I just put those two and I simplified, but you can put them together, hopefully, and then you can compress into one email.
Yeah. So I mean, obviously, if there's no one's presenting and you want to send a link out, then you have more sort of freedom. But then there's also less to say. There's less content there, so it would just more than likely be a few words and the link. So I suppose it's less work for you as well, Rajan.
Oh, thank you. There's like a template. All we need to do is change the date and put the link. Essentially. Everything else remains the same.
Well, yeah, but I mean, yeah, within reason, there's always going to be some small changes, but as long as they don't get out of hand, that's
exactly
just the way it is. Okay,
it's
so
kind of official, it becomes more official type of thing because we eventually hopefully go into in-person Hawaii meeting, things like that, hopefully next year or the following year, and we want to set the stage. And we are talking, Gerd and John, Christopher and I were talking, I think a couple of, either the last one or the before that, about compressing all to like a movie type thing, about 16th century to 21st century, all over YouTube, very similar to Oppenheimer, but more on the physics side. And so people, when we are in person, we can play it out and then give the gist of what was going on from Galileo onwards. And maybe somebody who knows very well why Galileo himself started the whole thing, because, how the physics started and how people started adapting the mathematics and everything, the equation of state, and became very important later on for industrial revolution and all the things that happened. And also development of technology. I mean, they didn't go hand in hand. I think they were like art. There was art of the industry making things and everything, but they combined together. The physics became integral part of that with maths education and everything. Electromagnetism, like Gerd was doing electrical engineering, and now IT with ChatGPT that Christopher is doing. But John is talking about the traditional physics, which is the normal physics. Yeah, normal physics that we have to understand.
Yeah. So you talking about like some sort of history of physics from
I
guess.
Yeah.
Well, that's
onwards.
And would you do that as you'd want to create maybe a YouTube video that you're going to edit and then upload?
Yeah, we can do that. Yeah, that would form the basis for the movie kind of thing, like episodes, like 10 episodes or something we can do, or less if you want to. I think it would take that much time because each episode maybe like 2 hours, 2.5 hours, typical movie. and so people, you know, you
prefer to do it in this kind of format, so you don't have to edit in images. You just maybe do a presentation on what you're thinking, or
yeah, we can do that after I think after the New Year we'll do that. I don't know, the holidays are coming in. I plan to continue. You know, I think it's a good idea to continue. Whoever is present, like next week also, it's a holiday time here in the US. May not be that much.
Thanksgiving or something?
Yeah, Thanksgiving time.
Oh, very nice.
I think, yeah, we'll have like an hour, 1 hour. There may be people coming over, but I don't want to skip meetings. You know, we'll have at least half an hour, 1 hour. So every week we'll try our best to continue, even during the holiday season.
Yeah, and then the first week in December, then we should have. Yes, exactly. Yeah. So the 2nd of December will be Andreas, unless there's a change. But it looks like that's on. Is it the electromagnetics of gravity or something along those lines?
Yeah, I think I had to change because I thought he's going to present on based on his presentation. But you said you talked to him. He's going to present on the basis of the discussion that's going on. The cause of electromagnetic gravity. Right?
On one of his papers, which has the same title. So he said it'll only take a half an hour to present the whole thing, and then we'll have time for questions, maybe another 45 minutes to an hour. So
that sounds good.
Yeah, so it won't be that long, and but it'll all be in German. So myself and yourself, will.
German.
I don't know about English. John, do you have German or probably not? I don't. But
no,
obviously,
no, not really.
Even I don't.
I can read it, but speak.
Yeah, very good. Actually, that's impressive because German and English, I just don't see an awful lot of connection between them. Like I could read, you know, French and Spanish and Italian maybe with the help of a bits of translation, but mostly because they're Romance languages, a lot of the words at the high level are the same as what they are in English. But when you get into German, I find it a lot trickier. Although I admit I haven't read a lot of high level stuff in German, so maybe I'm wrong about that. But this would be a good time for Gerd and Christian to shine. If they attend, they'll be able to listen to the lecture and probably engage in questions with the speaker much easier. So that's good. But for the rest of us, it's going to take a few days, I think, for YouTube to, it'll take all the text and translate it into, or take all the speech, translate that into text, and then I'll be able to take that and translate it into German, and then I'll have to upload it as subtitles, or maybe there's a way. Well, actually, before I look, I'll have to look into just how YouTube, whether it facilitates instant translation of subtitles into English.
Yeah, that's what I was thinking. That will be great. There's a instant translation, stuff like that.
Well, like I said, it won't be instant on the screen. It will take a few days. It will take at least a day to process, I think, because of a backlog of videos. And then after the system processes it, maybe there's a way to set it up so that it'll translate it into English straight away, or maybe I have to go through some steps. I don't know yet, so we'll find out. But I have to make a note of that to look into that before the event takes place, because if there's something I need to set up beforehand, then obviously if I miss that, it won't go through. But either way, it'd be nice to have a video. We're open to having videos in different languages, you know, if it helps people. Remember, was it Corrado Massa? He actually did his entire presentation in English, which is impressive because he didn't really have any English. But I was nearly like, he could have done it in Italian. We could have translated it later. But that's the way it goes.
Another possibility is that if Andreas or the speakers who are coming in the future can send a transcript of their talk, that transcript then can be translated.
That's a good point. Yeah, I was going to ask him about that. I suppose, it's up to him whether he wants to be stuck to a script or if he wants the freedom to kind of ad lib.
That's true.
And it's probably usually better to be able to kind of freestyle your thoughts. You know, it comes out less stilted. But I guess some people are like really, really prepared, and they will script every line of a presentation. And so if that's his style, then great. We can. I don't know. It'd probably be the same thing though. I'd have to translate it and then figure out. You know, to be a similar process, I'd still need to figure out how to upload those subtitles then, you know, and overlay them over the video. And if he goes off script for any reason, then those subtitles will be completely useless. So yeah, but that is good thinking. I might ask him about that.
Yeah, many of us, like especially John, has showed us, you know, he prepares a nice PowerPoint and very similar, you know, before the thing. Of course, he has all prepared. I also, I think, tried a few PowerPoint. You also had PowerPoint. So that type of presentation can easily be, I think, it can be in German, but he can translate equal, you know, on the side, translated to English, that type of thing, or a transcript, either one. You know, you can find out, Christopher. It's okay. Either way, it's okay for me.
Yeah.
It's a good to have original thing. Yeah.
Yeah, it'll be up to Andreas on that front, and also how the system works. You know, whether it even allows for to upload subtitles beforehand so that it plays over the screen. I don't even know how you'd go about that. I think it would all be post-production. That would be my guess.
Yeah, that's fine. Whatever works.
Yeah. And then we got a couple of comments from Emmanouil on the last live stream, which was nice. And,
yes.
Yeah, because I think he's fairly interested in that, and he posted some links and his own kind of thoughts. Because I think he's working with quantum, or like vacuum and gravity and inflation theory. So he was interested in the idea of the universe being able to expand in a single day, which is was part of my talk. So yeah, that was good. So and then I kind of just commented back, because there was one of the questions John had actually. So his first question was about forces, and you know, I wasn't really prepared to discuss forces the last time, but I did kind of hint at my solution by mentioning fictitious forces. I kind of wasn't, I hadn't really properly formulated it in my mind, so I didn't want to kind of speak off the cuff. But you know, but yeah. So essentially, what the idea is let's say the you know, you have the Big Bang, so all the galaxies are spreading out across the universe, but not from a singularity, obviously, just from the inner sphere of the hypersphere. And when they spread out, it's I was making the analogy of a disco ball. You know how the lights hit the disco ball as it's spinning, and the lights reflected on the wall around the room are traveling, or appear to be traveling, much faster than the actual ball is spinning. So again, you know, the hypersphere is like the disco ball. The reflected lights around the room are the galaxies moving as they move outwards. So they're not really moving at all. And I also brought up the point, a number of people, like in the past, were talking about, well, more so like if you have a laser pen on Earth and you're shining it at the moon and you just move it a little bit, that laser pen is moving incredibly quickly across the surface of the moon. And some people are saying, well, does that break the speed of light? But of course, you know, it doesn't. So these galaxies moving out at terrific speeds, and the entire universe expanding to infinity in a day is possible because they're not actually really moving. It's just a projection that's moving. Also, then there's the issue of the sphere itself, because that has to rotate. And so the galaxies, in order for the projection to occur, I mean, or not for the expansion, the illusion of expansion to occur, the sphere has to rotate 180 degrees. So that speed is, I don't know, let's say it has a radius of around 50,000 megaparsecs or something. It's going to rotate in a day. So I've forgotten what the circumference is. I can look it up, but you could work it out. But you know, so the speed of any one galaxy moving from, let's say, the South Pole to the North Pole in that rotation would exceed the speed of light as well. But because the entire sphere is rotating, and the sphere is a hyperspace sphere, it contains both space and the material in it, then the whole of space will be rotating. So it's similar to the argument of expansion, that the universe can expand faster than the speed of light because it is space itself that is expanding and not the material in it. Therefore, it doesn't contradict Einstein's theory of relativity. The same applies here on the hypersphere. You can rotate the hypersphere at any speed because you're actually just rotating space. But then maybe contrary to some of Emmanouil's, you know, I think I mentioned it in the talk that this expansion would be likened to inflation or hyperinflation, something like that. In fact, I don't think it is anymore, or I may have misspoke, because the hypersphere exists prior to the expansion, but the tangent plane also exists prior to expansion, and the tangent plane is all of space. So there is no inflation of the tangent plane prior to rotation or anything like that. It's just always existed. Or, you know, it doesn't need to expand anywhere to create the universe. The expansion happens into it, and only from an illusory perspective, if you will. It's not really expanding. Don't think I have any other points to bring up on that, but essentially, therefore, yeah, well, what are the forces involved in such an illusionary expansion? And I think you could probably calculate forces, but like I say, I think it's unnecessary. We've almost removed the need to calculate any such forces. And any real forces that would be taking place, like, for instance, the hypersphere rotating, that's technically happening outside of our dimension anyway, in the fourth, you know, the higher dimension above us. So, yeah. So, and the energy up there is potentially infinite. So there's no problem with energy. But where was I going with that? Because I'm just thinking about certain different applications there that have come to mind. But yeah. So I think. In terms of forces, those forces will be sort of tangential to the plane. They wouldn't really affect what's going on here so much. But then if we think about it, because I remember John's theory about sources and sinks within the galaxies, and well, one of my main questions was, well, if you have all this material coming in through a source, where is it coming from? And, you know, the obvious suggestion would be another dimension, like something outside of our visual range and perceptual range. But of course, we were all agreed on that subject that would be outside the realm of science, like, because we cannot observe such a place. But I think now with this new model that I'm talking about, all of the hypersphere has to be embedded. The surface of the hypersphere, let's say, which is equivalent to the tangent space, has to be embedded within a four-dimensional space, which has an exterior and an interior, which are not accessible to us. So you could easily have, you know, energy, and like I say, there's an infinite amount of energy in this realm because of that could be deduced from matrix multiplication. Actually, you know, dot product and. Or not matrix multiplication, dot product and inner product. So, and the fact that they don't work in dimensions above 4D. So, that might be a subject of another presentation, because I don't have the information at hand here. So, well, I do, but it's somewhere else. It's in a notebook or something. Yeah. So we you know, we could have potentially limitless energy flowing into the universe through, like, essentially pores on the surface of the hypersphere from whatever medium it exists within. So, but again, like, that is just conjectural in the sense that we cannot actually access that. Although we do have the material flowing in, so yeah, I mean, there's, but that essentially is just material that's in the universe. So, but perhaps we can infer things from that about what's going on in the fourth dimension above us. So it's pretty interesting. And so that's really all. I think that's all I have to say on that subject. But, also, what we were talking last week about strong and weak gravity, I think, was something that you mentioned several times in some of your papers, Rajan, to do with. So obviously, you know, that seems to link up a bit with maybe MOND, modified gravity, because like when you talk about weak gravity, you know, obviously if we're in interstellar space, the force of gravity is fairly low, and then at the surface of a black hole, let's say it's extremely strong. So are those the kind of, you know, and then you were speaking about a gradient between those two. Is that what? Because that's usually what's meant by strong and weak gravity, I think. So I don't know if you could speak on that and maybe elaborate where your thinking is going on the subject. Also, I'm going to stop the camera for a second because, but I'm still going to be listening. Yeah. Rajan, you.
Rajan?
Yeah. Okay. Yeah. Can you hear now? Okay. So. That's a good point, a great explanation, very gist of the thing that Christopher said. That's a great thing. And just before I go on to strong gravity and the weak gravity, I just want to mention about what Emmanouil has put just now. I don't know whether what you had chance to look at, the superluminal dark space time, about a new one. I think he has put a nice figure. I think it may be corresponding to what Christopher was saying. He's saying there's a quantum entanglement between the two phases. One of them is the superluminal thing, which is non-tachyonic but superluminal. The other one is the Lorentzian, invariant space-time, which is our subluminar or luminar. That's where we live in. He put a nice flow chart, a graphic that shows how they flow into each other. I think, how they're in quantum entanglement. And I was thinking about Christopher's thing. I don't know if it's a directional or not. I think directionally invariant, probably. The hypersphere sitting on top of the tangential space. That's just for reference. But I think it'll be invariant. Doesn't matter how we orient it. It could be on the side or the hypersphere could be at the bottom, and then so it's directionally invariant. We cannot, only for our explanation we are using it, I would think, but it should be invariant. I think there's a lot of things that what was that Nobel laureate Frank, I forgot his last name. Yeah, it sounds. We'll check. Dr. We'll check. Yeah, and they are all put a nice thing about projection into two-dimensional, multi-dimensional, and how we look into, how we'll all look like. It's like cartoon figures that's shown. So it's kind of very similar. And I have to agree with Christopher in the sense that the four-dimensional, but I would just qualify a little bit, saying that the four-dimensional space or toroid, the hypersphere, is not where we live in, but it contains all the information. And we live in Euclidean, like John is saying, the Euclidean tangential plane. We live in that, but the information flows from there. That's one of my main things. Information flows from there, the hypersphere, onto our tangent plane, and we create the clocks. The clocks are created in the Euclidean. And I don't think clock has much meaning in that other one. is more geometrical or topological, whereas the clocks are created here. So the information flows into us, and the entity, in general, entities exist in environment, whatever the environment is, could be superluminary, whatever, and we are the entities, and the entities form, and I have a key that will explain that is formed from the whole PDP mechanism, for example, which is an particle, and that it creates eventually the clocking mechanism time. So time starts flowing only then. And like Emmanouil said, that I think it corresponds to that condensate, like condensate evaporation. So it's like superluminary condensate, and your evaporation of that and go into the sublunar through vacuum. Vacuum holds the speed of light constant. So the particles will particle will start coming out due to the hot PDP mechanism, which is unparticled. And my recent CJPAS papers essentially emphasize on that, and I give some schematics how that could be happening. And then it forms the particles and it jumps out from the vacuum into sublunar space. So that's when the entities are really formed, like critical nuclei and things like neutrons, the neutron particles, which will start, the fission reactions and create, all other particles, like even up to protons, it's like positron, electron, but it stabilizes there and forms atoms. And like hydrogen is the simplest thing, and then isotopes of hydrogen, which is the main fuel that creates all the stars and everything, and things like that. But there are a lot of interaction because it goes into the condensate as luminar space or sublunar space, but it can actually go back and condense back to the thing. So there is a cycle that goes on. So there is evaporation and condensation, much like we see, like from the sea, the water is evaporating and then it goes back and become condensate in the sea. I mean, it's a picture that we actually extend to a larger global sphere, because whatever we see is what we project a lot of times. Whether that's completely true or not, we don't know. But that makes sense for the physics, that the small and the large have a lot of connection. Like we said, initially, that the atoms, the electrons orbiting the nucleus, very similar to how the Earth and the planets are revolving around the sun, the solar system. So they have one-to-one correspondence, kind of very similar. So the big picture and the small picture. But the problem comes from the quantum. When you go to quantum level, everything kind of breaks down. All the physics kind of breaks down, and that was the big, disparity between Bohr and Einstein type of presentation. So that's why the gravity aspect becomes the bigger thing. So that's what I was considering about the weak gravity and the strong gravity. So the string theory helps that. So wherever light is weak gravity, kind of, is a thumb rule that has to be proven. But I think that's a thumb rule, I would say. Wherever light is, it's a weak gravity thing. Like up in the space, in astrospace, wherever the light is more luminiferous type of thing. It's weak gravity. Where it's like black hole thing or dark matter, it's strong gravity. So the strong gravity prevents light from escaping. Like I think Emmanouil talks about these. They form a separate de Sitter space. So they contain within them that, so we cannot see that. Okay. So then we are, according to that, we are on the anti-de Sitter space. And for us, that other phase is like anti-de Sitter space. But so each one is enclosed in its own de Sitter space, but they can quantum entangle. That's how they communicate. But that's all. So the dark matter we can never see because it's self-contained. It's like a black hole, like I said, the black box. The black box is something we cannot see. right?
Yeah. So you're saying there's like de Sitter space with entropy similar to, and then the black hole maybe more like anti-de Sitter space. You'd have these two kind of de Sitter spaces. That seems to be
yeah. So the de Sitter space itself is like a black box. The black box is a much general thing. Like Gerd was mentioning about, we are inside a supermassive black hole. So that may be our aspect, our universe, but that may be communicating with the other one, which is a dark matter phase, like dark matter superluminous phase that Emmanouil is talking about. And it may be corresponding, I'm not sure, you got to look at Christopher's hypersphere, maybe something like that. And that is,
I think the dark matter and the there is a connection there to the hypersphere, I think. But just to go back to some of your other points that you made about, well, actually, one point that I didn't make previously that I kind of forgot about was, if you're rotating the hypersphere 180 degrees, and then you're asking, like, you might ask, well, how does that happen? Like, I'm thinking that it would be along the lines of something very computational, like you just, like I do when I'm trying to create the model on a computer, I just type in 180 degrees and hit enter, and it does the rotation. So it would have to be something like that, very precise. And there could be a reason why that is taking place outside of that, but I mean, it depends on your philosophies, I suppose, whether you're talking about something emergent or not emergent, like kind of more simulation theory, which is what I'm thinking about. But then if you're talking about invariance, that's kind of interesting because, like I mentioned, the original model was called the unique hyperspheric model. So it was invariant in a sense. You could have essentially everyone has a unique hypersphere surrounding them, and as they move, the hypersphere moves with them. So the metric contorts in the direction of travel, but expands in the opposite direction. So that creates distortions in the celestial sphere, like Lorentz transforms. But then later on, I was thinking, well, that's a bit messy, because it wouldn't just be a personal hypersphere for each person. Any object that can be accelerated at the speed of light, well, not that any object can be, but towards the speed of light, let's say a fraction of it, would need its own hypersphere. So, and that's legitimate, kind of proposal. That's completely legitimate. But I'm thinking now, then I was thinking, well, maybe we don't need that. But yeah, you could do some interesting things though with that, because the hypersphere, I'm thinking, and I don't know this for sure, but I think if everyone has, or if everything has their own personal hyperspheric reference frame, then the metric on that sphere will be different to the overall metric of the entire universe. My thinking is it will probably be something like larger metric on the bottom here when you're not moving, and then as you go up the side of the sphere, the metric lines get closer until you reach the equator, wherein they become infinitely small. So that's the speed of light. That's full Lorentz contraction, and then they begin to expand outwards again, and then obviously the opposite would happen the other way around, contraction and expansion again. So yeah, well, that all links into, so if you're halfway up the hypersphere, your own personal hypersphere, you're at the speed of light. If you were to go beyond that, then we could kind of partition the sphere into different sections, like real numbers, imaginary numbers, because one of the consequences of some of Einstein's equations, or maybe Lorentz, I'd have to look into exactly which ones, but when they've extended it beyond the speed of light as what would happen to time. I think time it goes into an imaginary phase if you go beyond the speed of light. So that would imply that when you go above the equator of the hypersphere, you know, your hypersphere is now tipped over, then you're in imaginary time. But then as you go beyond that again, you move into negative imaginary time. And then, so once you cross the horizon, or the equator, sorry, you're expanding back out, and you're no longer contracting, but you're going to expand in imaginary space, essentially. And then time will reverse, and you'll begin to shrink again, and then time will go back in a normal fashion, but you'll be expanding in a negative real number thing. And so that's just an extension of the concept there. There's more to that. It gets a bit more complicated, and I don't have all the details at hand, but that was just a quick sketch of the concept. So it'll be interesting to look into that. I think there's something to do with Mobius strips and all, because you can partition the entire unique hypersphere into fundamental domains of both laterally and then, how do you say, the other way around. So it becomes like a grid on the hypersphere, and each of the size of each of those blocks will be, you know, a 0-degree angle in the center, but obviously not 0 on the edge. But I don't know, so I haven't calculated that to find out what size that would be. But yeah, so to be the same process then, I think, moving from one dimension, like one universe, fundamental domain on the sphere to the next, you would have contraction, then expansion into imaginary time, and then a negative imaginary time followed by negative normal time, which would just be a slowdown to a stop, essentially. So I think what I'm saying is that you cannot go, like, going twice the speed of light is equivalent to standing still, essentially. I think, but I have to, that seems reasonable, but there could be some other consideration that I'm forgetting this juncture. So yeah, and on top of that then, Gerd, you published a new paper on possible, was it limitations of the metric universe? There was, you're questioning why certain values aren't exact, I think, in your most recent paper. So could you summarize that, or if that's possible? Yeah.
What's the question?
Oh yeah, your most recent paper. So you're looking at it's obviously the metric universe, but it seems like you're suggesting that, you know, that the constants aren't coming out exactly right. And so I was just wondering if you could summarize that, some of the ideas in that paper, what you think is going on, why they're not coming out right, or what you're doing to solve the problem.
Sorry, I don't understand the last question or the last sentence.
Yeah, just in general, like what is going on there with what do you think is happening with the discrepancies between the constants?
What is happening? The constant depend on the frame of reference. Most of them. Only the constants of subspace, which are except the constants of subspace, which are real constants, and you cannot leave the space because we are living at the event horizon, and if you want to leave, it's in future, but you will travel with the event horizon to the future, but you cannot go beyond.
Yes.
Maybe with some sheets with no.
So
imaginary time.
Yeah, the whole universe then, at each instant in time, you're saying, is an event horizon. It's not just like where we are specifically on the surface of the Earth or anything. The entire universe.
The surface we're living on is an event horizon, but because we are in a four-dimensional universe, the surface is not a surface, but a space.
Right, so it's basically the same as what I'm talking about in a sense. It's the surface of a sphere, except well, I'd explain.
And there is no dark matter. No, there is no dark matter.
Okay, well, yeah. So just maybe get ahead of ourselves a bit here, but what do you think about the idea of a tangent plane then projected? Wouldn't that solve the issue of expansion, or I suppose that mightn't be an issue what you wish to resolve, because that would remove the metric?
There is not only an expansion, there is also a propagation, because space is a wave function which propagates in subspace with different propagation speed.
Okay, well, let me ask it another way then.
It depends on the frame of reference.
Yes. Well, I think this was actually a question Rajan put to me before about my model. He was saying, well, space is flat. So if you have this curved sphere...
most of space is flat, but at the edge, or it's no.
Is it hyperbolic or something, or
not? No, at the center. It's not the event horizon. The other horizon. What's the
particle horizon?
Particle horizon. At the particle horizon, there is space is not flat, but only in the nearest vicinity of that.
Okay, so that area though is like we were to discuss the hypersphere. All of space exists on the hypersphere surface. But this particle horizon point is the zenith. Is it the North Pole? The top part.
Yeah, you can see it as, but not as Earth, but it's an approximation. Yeah. Yes.
So that's exactly what I'm saying. But I'm saying that at that point, there is a projective point that is projecting that point to infinity.
But I cannot say because the event horizon and the particle horizon are connected in back. Maybe or maybe not. Maybe that that the particle horizon leads out to outside of our like at a black hole. Yes.
Yeah.
It's like
Yeah, no, that is interesting. I mean, I think there's even a model of de Sitter space that kind of does a similar thing. They have like a sphere and then a black hole at the top or something, and then a kind of a tunnel going back down to the stars.
Like a horseshoe magnet.
Okay, yeah. I was thinking it would topologically be more like a torus.
Yes, a horseshoe magnet, yes.
Yeah, but so you have the torus, and then you have, I think, your model of the hypersphere has some connection with light going out and bending back around. So it's a bit torusy. It's similar. I think you had a similar model to Emmanouil about a toroidal kind of electron, but for the whole universe. Yeah, well, so, I mean,
the electron is a good example, but you must say that the electron is rotating around 3 axes.
3 of them, yeah.
Yes.
Okay, because of like maybe SU2 symmetry and all of that is important. But okay, so let's say we have this point at infinity, which is connecting back to, which is a particle horizon. That's connecting back to the event horizon. But previously you stated that the event horizon is everywhere in the universe. So this point is connecting back to every point in the universe, correct?
Yes, that's why we are living at the event horizon at the same time. That's the reason that there are such special effects like entanglement and so on, because it's the same time, and you can then some actions may propagate instantaneously. Yes, because it's at the same time. But there may be some other event horizons inside. Maybe, for example, black holes.
Yes. Okay. So, yeah, I mean, you see the connection there with what I'm suggesting in my model. If there's like a projective point, a light source, then that point is your particle horizon. The rest of the sphere is the event horizon, and everything on the sphere, or let's say everything on the tangent space, is connected to the point at infinity, projective point, as through everything else on the hypersphere, which is equivalent to your event horizon. So every point on the hypersphere event horizon is connected to the particle horizon projective point. So
yes,
the same
maybe.
Okay. Well, yeah. So I would.
At the Big Bang, at the time of Big Bang, all has been at the same point, and through expansion, but they are already connected with each other.
Yeah, well, I'd agree with that as well, because, well, I would say that that's still the case now. Like everything, well, in a sense, I mean, if we think about, maybe that's not actually true, because there is material, I'm suggesting, on the surface of the hypersphere, and it's being projected from the top onto the tangent plane. But if it was the fact that that material on this hypersphere was also being projected from that point, then it would suggest
I cannot say if there is a projection or not. I know.
Okay, but yeah,
I don't know.
Maybe
Like
or if everything is projected from that point, but also exists at that point, then everything still exists as a singularity as we speak. You know.
But there is not a singularity with 0 or because there is a smallest length of this because of the subspace.
Oh yes, so that would be like the Planck length or something. Smallest length is a Planck length. Or, okay, yeah, well, I mean, I suppose in my model, it's like an infinitely, it's a mathematical point. So it can be infinitely small, but as long as it is small enough to be so that the projection, the shadows it casts are very crisp, it doesn't really matter if it's, for me, if it's like infinitely small or mathematically precise or just Planck length. I don't mind too much about that. I suppose like another potential aspect of my model with the hypersphere is that the metric gets smaller and smaller as you go up, and possibly everything is getting denser up there as well. Energy is getting higher and higher. Right.
Yes,
so
yes.
So,
but it's because of the subspace, there is a minimum length.
okay, but do you not go for the
and maybe that the subspace exists also outside our universe, because our universe is expanding and propagating into this subspace. But the subspace is not a space in a priori. Yes.
Right. So is the subspace in your model let's say you have the hypersphere and it's embedded in some sort of surrounding sphere?
Yes.
That is the subspace that you're referring to.
Oh,
okay. Okay, fine. That's no problem then. That makes it a lot clearer as well to what you're suggesting. Because, yeah, my hypersphere would have to expand into the subspace as well. I'm just suggesting that it stopped expanding at a certain point, and then will.
Yes, I know you have a different hypersphere like me.
Yeah.
Yeah.
Cool. So, and let me think. Yeah. So with my model, then I'm thinking that material that's far, like way up the top of the hypersphere, could be really small. So like stars and stuff up there could be very small, or galaxies even, because they're squashed into the metric. And they could get to a point, like there should be a point along the hypersphere where we cross maybe into you know, the 10 to the minus 16, you know, kind of values of like quantum level, and then even beyond that, potentially beyond the kind of Schwarzschild radius sort of limits and Planck length. Obviously, you wouldn't suggest to go that far, but you know what I'm saying. So basically, we're talking about things that could be compressed to very small sizes. Now, in my model, those things will be reprojected back out to normal size.
Well, yes, but in my model, the quantum level is also a function of frame of reference, and in reality, the particles, like electrons, are very very small, smaller than we can as they appear, about 10 to the 60 smaller, and you can say it's like a projection through a lens, because the wave, the metric wave field acts as like a lens. We observe the particles through these lenses or lenses in the and the lens is about the Planck's minimum length, but the Planck's length is also a function of frame of reference.
So these lenses, is it a bit like with lithography, where you can project something smaller?
And because this wave field is schwingen, das heißt das. There is has frequency and amplitude, and the amplitude is in the it's like Planck's action. Yeah, yes. Planck's. What's the name? Planck's. I don't.
Yeah, I'm blanking on that as well. It's Planck's constant, no, but the reduced Planck's constant, but H bar.
Not H or H bar. You know. Yes.
Okay.
What's Planck's?
produced.
Planck thinks of action. Ach, was ist denn das?
Energy, time, action.
No, the Planck's constant. What?
Yeah, H is energy times
Planck's,
time. Energy, integral of energy and time.
Yeah, what's the name
constant.
of the second name? I forgot the
Action.
Yeah, what of action? Planck's Dingsbums of action.
The field of action?
No, not field.
The
quantum.
Quantum of
yeah,
action.
Quantum.
Right. Okay.
Planck's quantum of action is because that's no. The wave function is Planck's quantum of action, and quantum of action is not no, it's no an effective value of that function. Yes, and because that wave field is schwingen, oscillating. We cannot measure some subspace or no some values with die unscharfe Relation. Was war das? One moment.
Then after this, if we can take like 15 minutes break.
Die unscharfe Relation.
Okay.
Ja, jetzt hier. That's a reason for the uncertainty relation. Yes, because that oscillation of that metric wave field. It is like you have a camera, but the camera is not it's moving or swinging. No.
Okay. Okay, so this is why
you cannot fix your
frame of reference.
What?
The frame of reference is also changing.
No.
Cannot fix your condition.
You cannot make a sharp photo.
Yes.
Okay.
Well, that is like
your camera is moving. Yes. Yeah.
Okay. So
yes.
Yeah, that's cool. I like that. It's kind of
that works.
I think that was who was it? Heisenberg also had a similar analogy for why you could not resolve a particle's position and momentum at the same time because of this aperture function. But also, I would say that's interesting because you know, I also, prior to coming up with the how do you say anamorphic universe model, I was talking about using projective geometry to explain or to model, I should say, the uncertainty principle. So yeah, I'd agree. Projection has some role to play there. So Rajan, were you going to say?
We can take about 15 minutes break or something.
Okay, fair enough.
Okay.
See you guys.
Okay.
Thank you. Thank you.
Yeah, thank you.
Thank you.
Hi, Christopher.
Hello.
Hi. So Gerd has not come in yet. I don't know whether Gerd and John has left, but
I think I think they may have done.
Oh, that's fine. Yeah, so we can also wind up in an half an hour, 1 hour. Yeah.
Yeah, we wind up quick enough because well, yeah, might as well do some stuff. But
yeah, whatever. I have about an hour or more. Yeah, we can continue. Yeah, I think so. I will do is the email. I'll write down what you mentioned about compressing the email. I'll put the email and send to you as well as other people. But then you can make something, like a form or template from it. So we can just change it. Or there's a link automatically. I don't know if it's possible that whenever you change the YouTube, it automatically, I don't know whether you have like a program or syntax or coding, that automatically adjusts that and sends email. I don't know if it's possible. Otherwise, fine. Manually is also fine. So we have a customized touch to it. But mainly, all we have to change is that everything will be the same, so people can see in one page what's going on. So that kind of thing. I'll try to put them together, and you can probably modify that.
Yeah, well, I think Manuel's main problem was that he didn't get any notification about the presentation. But I think really, from my perspective, I was just because I'd mentioned it so many times in different different lives.
No, I kind of mentioned in that email that you have mentioned before, but we don't know. It was on the spur of the moment. Even I didn't know you are going to present that day, but I know you are going to present it because you have been talking
I was I was building up to it, but I had other commitments. So, yeah, I was working away on it, trying to get it ready, and then, because it was so delayed, I just presented it when it was ready, kind of thing. So there was no, I suppose I could have mentioned it, but
that's fine.
Yeah,
in the future we will try to put and then if we don't have any, we'll just say there may be, we can put like a waiver or whatever what we call as the disclaimer type of thing. You can say there may be unannounced presentations in some of the sessions. You can put that like a small note in there, that one. So that people know that occasionally somebody may present it. That everybody may not be able to be present, but the transcripts are there. I mean, the recordings are there. So the YouTube, live thing, of course, is better because you have live discussion. And Emmanouil is not able to be present in all our talks, but he will come when Andreas comes or somebody presents. I think that's what you want to do, formal presentation. And yeah.
I suppose we could have just a statement like upcoming presentation, blah, blah, blah.
Yeah.
And then give maybe give it say, oh, this will be in 2 weeks kind of time or something. And then, or if it's delayed, 3 weeks, and then it would happen or something.
Yeah, it's like expectation value. We are expecting that, but it could always change.
Because of all these other commitments, I have write papers and stuff like that. So if something like college work would take precedence, I would have to do that first.
Oh, of course. Yeah. For me also, there are things that come. So how is your PhD? Is it all in a smooth, flow type of thing?
Yeah, I'm working on a paper at the moment. So I'm just getting feedback from my supervisor on it. It's
like imputation, like data modeling, right? Data modeling, or
it's anomaly detection. So I'm just sort of going back to what I started on and writing a paper on that, which is a bit tricky because it means kind of going back in time and looking at older work. Should have sort of been writing the papers as I was going, but just wasn't in my mind to do that. So, but I'll get this one done, and then then
not very similar to what you are presenting earlier on invitation, as some other things that you are mentioning about the different models and different way of doing it, and you come up with way of amplifying the signals.
Oh yeah, those kind of things. Yeah, it's moved on from that actually. That was like later research, and then since then that's gotten a lot better because I ran some of those programs again on larger data, and they were really slow. So I've come up with another way, sort of how would you say, sort of
tabletop
model, taking a detour around the more heavy computational aspect and but still getting the same or better results. So that will be the next sort of phase to do. I probably won't write a paper on that subject, but I will include it in the thesis because that's sort of an important part of theses, I think, that you develop something, then...
Oh, yeah. It's like real time, right?
What?
Make it more real-time monitoring than...
Well, what I'm thinking of is, you identify what the problem is, and then you resolve it. So exactly, more real time, so it doesn't have so you're not waiting for like forever for the thing to process. And so I came up with a couple of different methods, and then because people have been working on this subject for so long, a lot of if I come up with an idea, it's already been done by someone else, so that's fine. I just credit them with the idea, that kind of way.
Yeah, you are just going further, a little bit further, using
a little bit. Yeah, exactly.
Extending it.
Yeah, so they would have come up with their idea, and then they write the paper on it, and that's kind of it. Whereas in my work, it might be like a stepping stone from one thing to the next. It's just, so it's, I'm using lots of things that I didn't invent, even though I am saying, I came up with certain things independently, just thinking about it, but they're quite kind of straightforward enough ideas. But then it's good to read other people's, it's good that other people have thought about it, because then they add something to it that, resolves some problem that I mightn't have thought of, and maybe they do it in a more complicated way than is necessary or something. I'm not sure why they do that. They might have very good reasons, but I find so you'd have that, and then it would just be like a stepping stone to other more kind of original ideas. But as I say, they're all based on other people's work. I've very little it would be completely original, so it's either adapting or stuff that people have already done, which is pretty cool. And then the next big thing is to evaluate the models, see if it's possible to evaluate the two models, and then see if what the results are, and if there's any improvement between my model and previous ones. And then that should be it. That should be that paper done, and move on to the next one, hopefully, as long as it gets published.
Yeah, sounds good. So I was thinking further about what you mentioned. It is very important. I think I will reference because I'm trying to, initially we mentioned about writing a book. So somebody has asked me, because I wrote about magnetars with the manual, the same people have asked me, because they are going to publish it again free, mostly, except for the copies. So I'm thinking about information physics and my first other papers, and I had to make 2 more papers, and you know, I said that I'm going to write 2 more papers and then include all of them that book. And then later on, of course, we too are going to write about. Tentatively I come up with the title called, you know, your geometry of space and topology of time, and transformative physics, transformative physics. So it means that it helps us go further, you know, advance it, so we don't worry about what happened before, because we are going through 3210 logic, which means that all the previous one we can kind of put them away as trifles, or most of it. And true force, we can kind of filter it and then say, okay, moving forward, what we should do. So that physics will set the pace for our next thing. And what I find in that one, it's interesting thing that you pointed out. Thank you very much for pointing out that literature. I'm going to have that reference about time loop you mentioned. So independently, I came up with, I would say, independently I came up with a rotational time loop, you know, from my error signal analysis I mentioned earlier. And that when you translate it, transform it, you get a translational time loop, which is what that other person is talking about. I think invisible landscape or something like that you had.
Oh yeah, that work, yeah.
Yeah, I have to get that. You have the reference, all right? Did you show the reference, or if you have the reference, it can tell me. I want to put that, or I can Google it. It should be okay. I think it should come up. What's the name?
We got a question here from a commenter called Not Spider, and they ask, can you use a rotating magnet to rip apart a black hole? So that was I think
where did it show?
It just shows up beside. If you look at StreamYard and then in the comments next to it.
Oh, the comments. Live viewer, no, it is not shown. Let's see.
Live viewer comments show up on StreamYard. This is an example. Oh, maybe it's just an example. I don't know if that's a real comment or not.
I don't see that. I don't see it in my thing.
Oh, okay. Well, hang on a sec. I can check if it's a real comment. But, let me think. It'll take me a little while. So yeah.
What is it? What did you say?
Yeah. So the question is it possible to rip apart a black hole with a magnet? Essentially.
Oh, it's an interesting question.
Yeah, we got another comment from someone on another video, and I think they were asking to present their stuff. So I haven't gotten back to them yet on it.
In our let's see. So if we go back to our thing, it will show that there. Oh, it's a comment under another thing. Oh, the Markol has Emmanouil has said, congratulations, excellent presentation. Is that the one? The axis of evil WP reference. Universe expanded. There.
Yeah, so those are the how do you say? Those are the comments Emmanouil left. But there's another one from a previous week that you can look at.
The previous one, let me check. I have not been checking that. Thank you for pointing out, because
sorry, that was a bit of okay, sorry. So one from a previous week. Yes, if you can look back in time at previous comments.
Maybe it was.
Okay, so that comment is not a real comment, thankfully. I don't think it is anyway. It's just an example. So it's like
maybe far back. Maybe like a far back thing. Maybe like 3 months ago.
Yeah, I don't know how long ago that comment was. I can check. I go in.
I don't see any so far.
Gosh.
I don't know what day it was.
No, I can't, because you know how YouTube tends to block. For some reason, it's blocking me from. Doing it. Oh yeah, well, maybe I could just.
Yeah, you can go to another tab. Another tab. That's why I was see it.
I'll just turn it off for that. And don't know if this will work.
That command may be applied to micro black hole, because that's one of my the way I use it like Emmanouil about the vortex thing. So there, I think that command can be applied. Like, I mean, that may be happening with.
That comment is probably AI generated. It's not a real.
Like ChatGPT, that thing.
Oh yeah, you're right. So it was from 3 months ago. It's the first time I think. Oh no, wait a second. Oh no, that is a different. Where is this comment gone? Oh yeah, wait a second. Most of the comments are from Emmanouil. Yeah, oddly enough, that that comment has disappeared. Maybe the user deleted it. I think the user probably deleted it after we didn't respond.
I mean, it's an interesting question because I think the Hodge actually is doing that. You know, John's Hodge is a magnet that may be ripping apart the micro black hole. That's how we get the PDP mechanism to be activated. So that's an interesting thing. That's an interesting thought that actually the Hodge creates the magnet, dipole magnet. Now we say monopoles are going all over the place in the superluminal thing. It's chaotic, whatever you call it, superluminal thing. But it doesn't have any structure. But when they rearrange and they form dipoles, they form Hodge. That Hodge is the magnet that rips apart the micro black holes which exist within that superluminal, the chaotic thing. And they rip apart and they produce the PDP mechanism. So that's a very interesting way to look at the physics. And then, but like I was mentioning, you mentioned about the time loop. So when I look at my analysis, I found like I mentioned that you said what is the basis? The basis is the mesoscopic levels. I kind of assume that there is an alien Earth they have found, so it's a reflection back there somehow, and that time frame is like right now. So we go through different time loops. Right now we are in the time loop, 8-year time loop. From 1960 to 2040. So in that time loop, each time loop has its own characteristic. Like the time loop before that has world wars and all those things happening. And that's not happening in this time loop. You can see it's not exactly the same, but something else is happening in this time loop. And that's 80 years old and it has its own characteristic. And after 2040, there will be another time loop, which will be a little longer. Maybe, like 88 years old, I found. And that has a different characteristic. What happens from one time loop to another is that in this time loop, everything kind of resets. You can see the patterns resetting 1960. No matter what you do, you cannot change certain things. And also, in terms of money and everything, rich people get richer and all those things, and you cannot invert it. But that may not be necessarily true in the next time loop. Everything could get inverted. The people who are poor or that thing become rich, and people who are very rich now, they become very poor, and they may be behind time. Like I feel that I am behind time. I think the new time loop, maybe I will be ahead of time. The other people who are ahead of time now will be behind the time, things like that. So no matter what you do, you cannot change certain things in this time loop, right? Because they're special character. I think that's an interesting thing that I find, the cyclical. That's also connects to a cyclical type thing. that each time loop goes to a cyclical thing that, like cobweb, it keeps going through, and then the patterns keep repeating, like history repeating. So no matter what, like we mentioned about Israel Hamas war or something like that, that's happening. So these things keep repeating no matter what happens, and that's a very specific characteristic of this particular time loop. So I found that, and from my matrix protocol, that's how we come up with the delimiters, and each one is characterized by something I call metrics, which I derived like a code that's derived from their fundamental information, and there's an algorithm also I have found that works there. So that defines the range of the time loop, kind of. So the time
well, I was going to ask about the range there. So it seems like it's roughly like the lifespan of a human being.
Yeah, exactly. That's a good point. That's another thing I noticed. So right now it's like 80 years. That's a kind of an average lifespan of a human being. But the 88 years or 88 means that will the lifespan of the human increase to that level, another 8 years? That's an interesting thing to watch out for. I mean, statistics we can find out after 2040. Now, after 2040, I'll be much older, but you will be still in your prime, so you will be able to track that.
Well, yeah, maybe, but what about? Well, so when were you born, Rajan? I'm just wondering, just curious.
In 50s, late 50s.
50s, right?
Late 50s.
So
I'm the 60s. I'm the 60s.
You were what? You were growing up. You were born in the 50s, yeah?
Yeah, the late 50s, yeah. I mean, when the Sputnik, actually, I would say the year that Sputnik went to space. So I'm a space,
Oh, right, yes. What was that, 57?
Yeah. I was born.
Okay, very good. So you were born in the beginning of the space age then?
Space age. That's where it started.
So I'm wondering, are you linking the time loop to like roughly when you were born to?
Just after. I was thinking that it would be before me, but there are some calculations, certain things, mainly matrix protocol, which is information which contains both logic and language together. So the information I get is very fundamental. I test it, and it comes from some source, maybe divine or superluminal. I don't know what it is. But initially, remember, you showed also, it's very similar to the one people used to have. See, they used to see in the water, divine thing.
Brine.
That's brine, like brine solution. And I also had, when I was a boy, the teenager, I actually operated something that one of our things, the local. I think even in England they have. I don't know if it's called witchy wheel or whatever it is. So you adjust it, you do some mantra and things like that, and you put a steel glass and you hold it and say some things, and then it'll start going around. So you have to put all the alphabets, numbers, and everything there. It goes there, and you ask the question. You see, I see the vibration in my finger. It's moving by itself. I don't know how it moves. That itself is very perplexing. But so I know that it has some divine connection. So it goes around.
Is that called a
divine
Ouija
or whatever? And it starts answering.
Is that not a Ouija board?
Yeah, I think in England also they used to have something like that, very similar thing.
Oh, so you're saying that you have those in India?
Yeah, we had. I myself at home. Somebody came, and that person is distantly related to us. And I was a very curious kid, right? So that person said, "Okay, you're curious. You'll be able to do this work." So they showed me how to do that, and I was a fast learner, right? I didn't need much explanation. So I became slower now, I think.
But is it because what I'm wondering is that a traditional method of divination in India, or
no. So that's the problem. in India, so that's not considered part of priestly or godly thing, because some people doubt whether it has devilish connection.
So, oh yeah.
Okay.
Then you are
similar to what you are mentioning. Yeah. So yeah. Like
that is what it's called then.
Witches brew. Like witches brew and things like that. You know?
That's that thing has an odd sort of how do you say, origin, you know, because I think it was actually made by a toy company. I'm not sure the name, like Hasbro or something, some like well-known toy company. And so, but yeah, people do think because you're kind of it's connected to spiritualism and talking to the dead, which is, I think in the Bible, in the Old Testament, it says not to do that, as far as I know, or it might be in the New Testament. So therefore, people say, "Oh, you're not actually talking to the dead; you're talking to like demons and stuff." But it doesn't necessarily say that in the Bible. So that would just be people extrapolating, because there are actually scenes in the Bible where people do talk to the dead. They raise them from the ground. I think it's in the book of Ezra or something like that. Yeah, so they raise this woman from the ground. I think it might be a witch or something. They ask her questions. So it is something that is done in the Bible, but I think maybe you're not supposed to do it for maybe entertainment purposes or something. But I think the idea that there's like devils or something attached to it, probably not. Like for instance, I actually did that one time when I was in a house in the country. It was like a haunted, ghosty experience, and yeah, it was I kind of interested in it, so I was sort of open to the concept. But you do these kind of protective rituals, where your soul goes up to the light, or you imagine yourself going into this protective light, and then that sort of ends the that's supposed to bring the whole ritual to a close then, and you're protected. But for some reason, like when I imagine things, I tend to imagine them in quite considerable detail. So for me, it took like, I had like a long way to kind of travel to get to this light, you know, in the sky. I was imagining it being really far away. And I think everyone else just did it sort of quickly, you know, they were like, yeah, I've done it. And she was like, is everyone finished? And I was like, I didn't want to be holding everyone up. So I was just like, yeah, I'm done. So then when I went home later on, I was sitting by my computer in the hall, and I saw this like white ghostly figure just walk by behind me, you know? So I was like, oh, I brought the ghost back with me from the castle.
It's not an apparition or something, right?
Yeah, it was like, because I think the story surrounding the castle, there was a big lake, and these two lovers were, one was the prince living in the castle, and then the woman he was in love with was part of a neighboring clan, if you will, like a tribe.
Like Lock-in-War? Is it like Lock-in-War? You know, Lock-in-War, there is a famous English story about how he elopes with, you know, the enemy's daughter or something. That one.
Well, yeah, a bit like that. But this is in Ireland, you know. So, but yeah, so they're planning on eloping, I think. Yeah, because they're rival groups, and but then they're crossing the river and they both drown or something like that. So the kind of apparition I saw was like this figure of a ghostly woman kind of thing. So. But
Romeo and Juliet. Romeo and Juliet.
Yes, exactly. It's quite a touching story. So then I just went through the ritual again, and to make sure I completed it, and then that was that. So I also think you have to break the glass is another part of the. But I don't know. I don't know if that's effective, but I suppose it is in some ways.
Yeah. Yeah, actually, it's not all that bad, because at that time we are family together. So I am one of the younger in the family. So whatever I do, somebody is supervising me. Mother is always close to me. So when I was doing it, everybody was sitting around. I was operating it, but everybody was asking questions, and my elder sisters, my mother, and all the people were asking questions, and they are watching closely, because they don't want me to get into trouble. So they were very close watch. So because of that, but what happens is automatically you ask certain questions, you go around, certain very, you start, because we are a little bit, more curious intelligently, and then we start freaking into the thing. So it will start going around and finally stops. After a while, it will not work again. I mean, it worked like a couple of times. I think after that, it will not. And I have never been able, I forgot how it was, but I still remember some of the vibrations, and some of the things are actually true. So it was like giving like a predictor, it's like a prophecy type of thing. That, so I had not gone. I went to Greece to see Emmanouil. I saw, the Parthenon and all, but I didn't go. Another set of people, I wasn't at my reach party, but another set of people, they went to Oracle of Delphi. We want to go, but we didn't have time. So I think it may be like Oracle of Delphi, maybe working like that, or something like that.
Yeah.
So like a prophesier, or a seer of the future, things like that.
Yeah.
So I thought that was real power, and without that power, you are nobody. So now I'm trying to get back to that power. I think I resurrected many of those powers.
Very good.
But in terms of physics, so this particular physics is helping, and your thing has, you have a lot of new things that you actually propose, how to approach aliens, how to get the UFO, how to actually have the UFO experience. One of your books, I think you are mentioning, and you also done extensive research onto this paranormal phenomena, and even Sabina Hasselfield is saying now she's thinking that actually they could be aliens, they could be, she's open to the idea, and also think that, and one of the videos I say we are too boring, so they don't want to contact us, but they are there. They can get faster than speed of light, and we are not able to get information faster than speed of light. So I think that idea also emerges, kind of what you call is in agreement with many of the things that we are talking about. So it is not totally science fiction, or totally what you call a proof kind of thing, But I think so. That's why I needed physics, because we need some proof. Once there's a proof, I don't think people can deny it. If you can prove the pattern, that's why I'm thinking the if I can say the word correctly, transformative physics that I'm thinking of the book. Further than that, we will show proof. We actually show real-time things that actually will actually manifest. Will show the proof of a lot of what we are talking about. It's not totally, out of this world, just imagination, but actually born out of proper physics. Like when Emmanouil talked about it, I caught up on it, right? Many people said that this is all meaningless, monopoles and things like that, Aristotle. And they were trying to discredit us, some of the people. And he would have had a hard time, because his PhD thesis, I was in the halfway through, I think, when I met him. So he was quite interested, and he took a lot what we are discussing about. He actually extended that. So he was very bold in doing that. But whether he would have got his PhD because of this thing, he had to put back some other relativity things like that, because otherwise they won't accept it. So that kind of thing is that Emery Taylor, similar thing, but people are slowly accepting it. So now we are going to about Dirac. He's talking about Dirac thing. So, what Dirac was talking about in his thing, a special type of thing. So that's where I mentioned about oscillation. The thing is that I think it suddenly dawned upon me that the charge, you know, the fine structure constant, there's a charge, right? E square over something, hc and all that. So that's original. We actually re-derived the fine structure constant. I myself did that, and I think that's a very original thing. That's we applied for breakthrough physics and all that. But the thing is that hopefully next year again we'll apply. But the thing is that that E, the charge, does it depend on relativistic thing, or relativistic thing whether it will change? I think it will change, because the charge, when it goes to high, that you were mentioning with the Gerd, some discussion with Gerd just before the break about the charge oscillation. The oscillation of charge can happen at high speeds. So like you mentioned, so we cannot really resolve it. So the charge actually does not remain constant, for an electron charge, but when it goes through very high speed, the charge starts oscillating. That's my very similar to neutrino oscillation, very similar. But I think more generalized. If we generalize that, it could be true of electrons also. That oscillation will change the fine structure constant, because that E value in the fine structure constant, if it's changing, that oscillation may be very small, sinusoidal, very small changes, but even then, the fine structure constant really will not remain constant. That's one of the reasons I am doing general transforms, where I remove all the constants, all the mass, everything, only the time and scalar fields remain in that transform. Because these things can change. Even G, I think Andreas is talking, I know he's going to emphasize that, where G is not constant, the Newtonian universal gravitation constant, G will not be constant. And I probably, if he's talking about, I will have to agree with that. Over a period of time, it will change. And we can talk about neutrino oscillation. I think also that will change. But I think more generally electron oscillations of charge, which is part of the CPT problem, I think that also will change the fine structure constant. So which means that, you know, what Corrado, Massa was talking about and all that will come into picture. So we have to, you know, redo our physics, you know, because a lot of the physics is based on that. Even standard model, all that is based on these kinds of things, that the fine structure constant is constant. I mean, that, but may not be constant. So that's an interesting aspect. And your hypersphere model, again, I'm thinking about it. So, and then Emmanouil's the quantum aspect, where you have the dark phase and the light phase, how they are quantum entangled, how they can, you know, go from one to another like condensates. And then, of course, they are disconnected by themselves. You know, they are disconnected entities. And so I think it's all coming together. And my thing is that environment, there is a general environment. That environment may be superluminar, whereas the entity will be subluminar. So then that's Lorentzian. So which one is Lorentzian? Which one is non-Lorentzian is the whole question. So I think the subluminar should be Lorentzian invariant. speed. The speed limit cannot exceed speed of light. Whereas the hypersphere, I think it can go superluminar. So that's the only question we have to resolve, because you are saying that in the tangent plane, it can go faster than speed of light. It's not Lorentzian invariant. Where the hypersphere is Lorentzian, you know, the speed of light is going to be that.
Well, so yeah, true. Yeah, that is a good point. I mean, yeah, so it goes faster. The further you go out, the faster light gets. But then the question is, I mean, if you have you're saying that the model is invariant, the tangent space, like there's the center of the universe is everywhere. It's not just located in one position, then yeah, I mean, that's fine. I think that's from a relativistic point of view, that's kind of expected. Although it is a bit confusing. I haven't really thought about it that much. So, I mean, there is one theory about so like I say, I haven't really thought about these aspects too much, but there was one guy who had a geocentric model of the universe. And then he's talking about speeds of things that are, like, if stars or galaxies are rotating around the Earth, then obviously the further you go out, the faster they're going to be traveling at like ridiculous speeds. So similarly, I think he was saying that his sort of solution to that was to suggest that because space is rotating so quickly, it would be under a lot of tension, and then something that is, you know, more tense, waves tend to travel more, you know, they travel faster through it. So he was suggesting that as you go further out, the speed of light would increase. So therefore, well, slow down. But he was also just saying that since light is traveling at infinite speeds out there, essentially, then gravity is also moving just as fast. So that's why you have sort of instantaneous gravity across space. Now, I'm not sure if I agree with all of that, but there's definitely some sort of resonance with what I'm saying, particularly to do with the fact that the further you go out from Earth, the faster light is traveling. So therefore, the faster gravity would also be traveling. But the question I have is that, okay, light's traveling faster, but then time is slower as you go out. So does that not slow the speed of light down? Which would slow the speed of gravity down. So you just have the universe as it appears now, and you'd still be left with the same problems. Or is it that, or is it that like the speed of light is still very fast? It just looks slower because of something. Maybe time speeds up to meet the speed of light. But that doesn't sound right because of what we know of. You know, you have to keep all our ducks in a row here with the type 1a supernovas and the fact that they tick slower the further out you go. So those are. So what do you think? Basically, I'm asking you a question.
Yeah.
You've considered this before.
Yeah. See, I am more into now weak gravity and strong gravity. So what happens is the weak gravity. You have.
What would your opinion on that subject be?
Okay. So I think what happens is, okay, let me. This is what I think. You know, you go further in your tangential plane, for example, right? But I think what will happen is it will start curving around, and it forms like what Emmanouil is talking about, another sphere type thing. It forms another sphere. So you have two different spheres. So in that case, the speed of light can, you know, whether it's Lorentzian or non-Lorentzian is the whole question. So what detects that? How the light is going faster. So my thing is that the gravity, when it becomes stronger, it's much faster than the speed of light, like strong gravity. But the weak gravity, the light is controlling it. And it's controlling for light, I think the speed of light is the limit. That's my feeling. If it is faster than the speed of light, it won't be light anymore. It will be some other field, like gravity or some other field. So the light, the field of the...
Yeah, but if light is traveling faster, I mean, all you need to do, like, you just, you know...
it transforms. It doesn't remain as light. It transforms like Alexei is saying, like torsional or some other form of field.
But
so
I mean,
it converts
you
itself.
can have, like, you know how if you're traveling faster, or if you have a gravitational field, you have light comes in and time slows down. So it's all invariant. But you could also just say, well, time is invariant and light speeds up or slows down, you know, and that would be the exact same thing. So
yeah.
So
one of the things is the light itself is something you can see, right? So, but the light itself, I think it transforms. So it doesn't, you know, like energy transforms one form to another. So I think the field also transforms the light to some other type of field. So it may go like we see the mesoscopic level of the light, right? And that same light in the other, you know, the astrophysics, where astrophysical level much further down, the edge of the universe, it goes faster than speed of light, but it may not remain as light. It will transform to some other form of the field, and then it travels.
I think,
but it can retransform. See, it can come back depending on the environment. Comes back. Yeah. Suppose it comes back, it becomes light again. You know, you imagine. So it can transform something light to something.
This model, like the hyperspheric model, you know, light on the hypersphere is constant, but the metric is smaller. But it's just a projective thing. Like when you project it out onto a larger scale, you know, it appears to be moving faster. But from our perspective, that appearance is all that you need. That appearance then becomes a reality. But like in reality, like the reality of the hypersphere, light isn't moving faster. So it won't transform. And therefore its projection onto the tangent space won't transform. It will always just look like light. So that doesn't work in this model.
No, but a tangent plane, does it remain flat or does it go over period?
The tangent plane is like mostly flat. It's like nearly entirely flat. Might have a slight, very slight curvature.
At the edges.
The whole way out, I'd say once you get to the edge, it spikes. You know, it goes hyperbolic. There's like essentially what you could describe it as is like a meniscus, like the surface of water. There's a very slight curvature, but then at the edges there could be like a meniscus where it just warps upwards hyperbolically.
So it's like a ball, like you imagine a ball on a piece of paper, right? The ball is rolling on a piece of paper, flat piece of paper.
Mm.
Something.
Yeah,
like
I mean, to all intents, because you can never actually reach this meniscus I'm talking about, the dip in the water or of the tangent space is so minute, you'd probably never be able to measure it. You certainly never be able to measure the meniscus value, assuming such a thing exists. I think it does.
So the other aspect is the subspace. So there's a space between the hypersphere and the tangent plane. That could be a sublunar. That could be like a subspace, like vacuum or something like that.
Yeah, well, we were discussing that before, I think. That the light rays from the projective point move through all that subspace. In fact, you know, they're the only thing in there, really, I think, mostly. And so they move kind of, well, some of them are perpendicular, but they move obliquely, I guess is the word you could use, to the tangent space. But they have to be traveling, whatever is going on with them, they travel faster than the speed of light, like instantaneous, because they have to take information from the hypersphere to the tangent space. And then as they do so, so if they're projecting like a star, let's say, onto the hypersphere or onto the tangent space, then the force at which they project that at could warp the surface of the tangent plane, causing localized gravity. But this wouldn't affect the other idea that we were discussing there, that the further out you go, the faster light is, therefore the faster gravity is traveling as like a force. So that could still be instantaneous, while locally, you know, on the curve metric kind of parameters that we normally talk about gravity, that could still be somehow constrained to a
like black hole can form black holes on the tangent plane.
Yes, like I discussed last week with the quasars, which are believed to be black holes. Those are the reason why they're so highly redshifted is because let's say the hypersphere is so distorted at that point that they're actually closer to the point of projection than anything else on the hypersphere, on the surface of the hypersphere. So they're closer to the source of the light. So when they're projected back onto the tangent plane, they become larger. In effect, their shadow, the projection is larger, which means that the rays of light inside it are, expanded by the same amount, which causes them to look more redshifted than they are. And I did the calculations on that, so that, I did my best with the calculations, but it seems to me that you've got to be something like 0.5 megaparsecs into the black hole to achieve some of the redshifts that Holton Arc has detected. Forgotten what those values are exactly, but they're maybe 0.3, something like that, redshift values. So that seems to explain that, the anomalous redshifts of quasars and the lack of time dilation. So essentially these black hole quasars aren't as far away as their redshift would suggest. They're not on the order of the type 1a supernovae. And that explains why both have equivalent redshifts but have different time dilations. So I think that's pretty good. The theory is not just descriptive, it also has some sort of explanatory power. And that'd be similar to like Einstein's theory, just similar to this one. His one was a geometric model. So you could say, oh, it's a description of gravity. It doesn't explain anything. But then from that, we get, I suppose, descriptions of other things like black holes themselves. And then, so a description doesn't need necessarily not to have, it's not exclusionary that you can't have also explanations involved. I think, along with that, especially if you have a sort of a galactro or geocentric or galactrocentric model, then you do get a lot more explanations. But I don't know if everyone is. Yeah, it's an interesting one. So we still have to figure out which is the case on that, which is kind of funny. We're going back to those kind of areas.
Another aspect is, so you should have a source of light, a point source of light or whatever, above the hypersphere for it to project, right? Where does the source point come from?
The point is at the north pole of the hypersphere.
It has to be above that, right?
No, it sits on the sphere.
No, then it cuts through. How does it become?
It needs to cut through.
No. If you are at the North Pole and the light is now traveling this way, it has to cut through like a cord through the hypersphere. It has to be above that to make it, tangential to that thing, right?
No, it's allowed to cut through the sphere, yeah?
Yeah, it has to cut through the sphere.
It's allowed to, though.
Yeah, if you have the North Pole, you have the sphere, the North Pole is sitting there. Okay, yeah. So you have this curvature. So if you point the light is from the North Pole, how does it traverse to get to the
tangent plane in a straight line from every point?
Yeah, but at the North Pole, it can be tangential like that, right?
Yes.
But in order to project to the tangential plane down, how does it project? So the source, when you extrapolate the projection of the tangent plane, there'll be like a cone above above the hypersphere. You know, you draw the geometry. You see the geometry. You see that.
Think about it this way, right? So there's the sphere, point at the North Pole, and you have the tangent plane.
Yeah.
And then oh no, sorry, you've the tangent, and then the tangent plane at the bottom here, and the light rays just go down like in every direction. So if you're at the South Pole here, you're going to be faithfully projected onto the tangent plane because you sit on the tangent plane and the sphere at the same time. So that's where we are. But if you're further out, the light ray is going to be kind of incidental. It's going to be oblique, and the shadow, your projection you're casting will be slightly longer, so it will look redshifted. So that's why every direction we look in space, everything appears redshifted because of this anamorphic perspective going on.
But your point source itself, it's moving. It's not constant at the North Pole. It's itself is moving along the sphere.
It's like the North Star. It's like the North Star, you know. It stays in place. It never moves.
Yeah, but you see that, if I can draw that anyway. So you have sphere here.
Yeah.
You have something round. So if you have something round, I'm trying to see. And I don't want to draw on a piece of paper right now, but if I can get like a ball or something. I don't know whether I have a ball.
Okay.
What I'm trying to say is that if I'm understanding correctly, I can just draw on a piece of paper, maybe, and then just show you.
If you have a good enough marker, you could do that.
Yeah. So. So I'm just drawing a circle, you know, just a projection. I don't know whether you can see this now. This is your tangent plane. This is your tangent plane. This is your hypersphere circle. So it's like a projection. So your tangent plane, and you see that, you know, when you, from the tangent plane, when you project it back, project it back. When you project it back, I'm doing the opposite back. Okay. So when you go up there, you have like a cone about our thing. You see that? So this is your source. But you are saying that this remains constant here in the North Pole here. But if it's constant, suppose then how do I project it? When I project it onto this, how do I? So here is okay, on top is okay. But when I project the light from that source, I have to cut through the thing. How do I resolve that? You see that? You have to cut through. If the point source is remaining constant there, that's a cut through here. So if I project it, you know, to see that if I project from the tangent plane, trying to project it back, then you like a cone, there is a cone sitting on top of the thing. And this is the source of light. Let's say the point source of light. The point light source. So point light source is sitting there, but this is your North Pole of hypersphere. So that's your North Pole. So it's kind of shifted away from the North Pole a little bit for it to project onto the tangent plane when you do the geometry. So how do you resolve that? Are you there? Oh, Christopher, you are gone? Okay.
No, I'm on mute, sorry.
Oh, okay.
No, it needs to be on the hypersphere at the North Pole. And, you know, if
but
you
how
go
do you
back,
resolve? Geometrically, how do you...
Yeah, if you go back and watch the presentation I did last week, there's a lot of...
oh, you are saying it's going to rotate? You are saying this is going to rotate? So the North Pole is rotating to project it? It's like North Pole is rotating to sphere it? That's one of the things you have mentioned.
No, well, the rotation is just to do with the initial expansion and final contraction of the universe.
It's not happening. It's not happening all the time.
Well, I mean, it depends on your point of view. Like, if you think that there's this galactocentric or geocentric model, then the entire hypersphere needs to be rotating once every 365 days, or could be every couple of 100 million years. Depends on where you locate the center of the universe.
But you are saying the point source is at the North Pole. That's all. That's all the light is.
Yeah. So technically, if you were to travel out in to an infinite distance out from Earth in any direction, you would eventually... No, sorry, you'd never actually encounter the point source, But if you were to travel on the hypersphere up towards the north, you would eventually encounter it. And if you were able to cross through it, it would look like you'd gone, you'd traveled one direction in space, let's say to the east, and then you'd come out the west, You'd appear on the opposite side of the universe instantaneously, is the point I'm making.
So this is a rotating hypersphere. Usually the hypersphere is rotating all the time.
Well, yeah, but it would have to be rotating like the way the Earth is rotating. So the North Pole there and the South Pole are the axis of rotation.
I like this one.
So the equator is rotating faster than the other parts. And we kind of see that in, well, no, we don't see that in the redshift, but that should have, no, that wouldn't have an effect on the light speed.
Something like that.
But the other rotation, there's a what's the word? Kind of not a dual rotation, but a rotation through the z-axis, really the w-axis. So we have to remember it's a 4D hypercube. We're kind of thinking in 3D just for ease. But that 180-degree rotation through the z-axis would, that's what causes
the w-axis, like this one, w-axis.
Yeah,
like
yeah. So it's rotating
so
around
upside down. It's upside down.
Right. Yeah, that would be the expansion though. But the point, the projective point doesn't move during that rotation. Because if it did, it would no longer be projecting onto the tangent plane.
So the South Pole becomes the South Pole is on top now, right? It becomes on top. The North Pole becomes down.
The projection point doesn't. The actual projection point is sitting on the sphere, but it's not.
Not North Pole. Not North Pole. I mean, it's not attached to the North Pole.
Yeah, exactly. Yeah, the sphere can move without moving it. Yeah.
So then I think this will be more correct then. It'll be slightly above that, so that it can project it. So it doesn't
because it has to, anything that's right next to the projection point on the sphere needs to be projected to infinity, and that can only happen if the point is on the sphere.
So then it has to oscillate, something like that. Because I don't see how it can project when it's on top without cutting through the sphere. I mean,
It's
geometrically, it doesn't make sense. I went through your presentation, but I'll go through it again. But I don't see how.
It's supposed to cut through the sphere. If it doesn't cut through the sphere, it can't project what's in the sphere.
Yeah, that's what I'm saying.
So it has to
actually. Oh, it cuts through like that.
Yeah, just look up stereographic projection, and you'll see that it always
cuts through like that. Okay.
Well, the direction you're going is wrong because it needs to come from the North Pole. But I don't think you can see what you're pointing at. So
the North Pole.
Then now you're you're North Pole. Yeah.
And then
I don't know what you're drawing.
Yeah, let me get the sense correctly. So yeah. So if I'm here, right, then
it's like a cone, like you said. It cuts down like a cone, yeah.
Yeah. So suppose I'm here, right?
Yeah.
So then I come down like that. Oops. On this sphere. I mean, let me check.
Well, there's another issue there that we could just discuss.
Yeah, it comes like that line I have drawn, right? The line I have drawn. So it is like this one. The arrow, I'll put an arrow there. So like the arrow I've shown, so it comes down like that from the North Pole.
You froze there a bit. Hang on a sec. Okay, it's gotten a bit messy. I'm not entirely sure.
Let me draw another one.
Looks like you're drawing that line from above the tangent space, above the hypersphere. So that can't be right. It's got to be on the sphere.
So will it be like that?
Now that I cannot.
Will it cut through the sphere?
Yes, it cuts through the sphere. Yes.
Like what I have shown now, the other side.
Yeah.
Simplified picture. Okay, that's what I want to see.
That looks right to me. So yeah, if you just look up stereographic projection, you'll see that's just the normal way.
This is okay. Yeah, if it is doing that, that's okay because
yeah. So, well, you were talking about magnetic monopoles, and I remember I came up with a kind of a rough idea about if a black hole were to move up towards the North Pole on the sphere, and the let's say it's a bit shaped a bit like a trumpet, maybe, the black hole, because it's a point, it's a singularity, so it's like a kind of a cone, but a trumpet. So if the mouth of the black hole were to move up to the projected point, and the singularity was already located at the projected point, then they would join up and become like a closed loop. So this kind of reminds me a bit of, one of the postulates or tenets of inflation theory. I assume it's well, it doesn't the name doesn't really escapes me now, so it doesn't really matter. But one of the I guess because string theory had suggested that magnetic monopoles have to exist, but then where are they? So in one of the postulates, I guess, or one of the conclusions maybe of inflation theory is that they all get, as the universe expands rapidly at the beginning, all of the magnetic monopoles get thrown out to like as far as away as possible, so like infinitely far away. And that's kind of similar with these black hole loops, what I'm calling, I don't know, halo black holes or loop wormholes, closed loop wormholes. They'd have those would also, because they can only be formed at the North Pole, they would also exist at the infinite reaches of space. So the question I'm asking, and they would also could be tiny. So I suppose I did actually touch on this before, that they might be, you know, it could be the genesis of string theory in that sense, that they are like these toroidal loops of space-time that are very small, very far away, but also embedded in the North Pole, which is projected straight down to us. So they would appear to be like microscopic entities, or not, you know, even smaller quantum entities here. So they could be studied in that way. But then that would imply that you would be able to find monopoles here. So maybe that doesn't make sense, unless, I mean, if they are these closed, yeah. I mean, it kind of goes back to that weird AI question that was just automatically generated that we got about magnets and black holes, because maybe that's what sparked me thinking about it. No, it wasn't, but well, maybe it doesn't really matter. But you know, if does a black hole have a magnetic field? I guess it ought to, but at what distance? They do, right?
It's a vortex field.
Okay.
But the thing is that, my thing is that the vortex field, right? What happens is the monopoles get thrown out because of centrifugal force. So they go at the edges.
Yeah.
So the monopoles will stay at the edges, and then they form, like you, I mean, that makes sense, like wormhole, which is like a dipole. Suppose you have a north pole there, or at the centrifugal, at the surface. You think of a de Sitter space at the inner surface of the de Sitter space. Inside of that, when it's thrown out, so here you have North Pole, you have South Pole, and they form like a dipole wormhole. You know,
yeah.
So they connect with them like a string, and they're instantaneous because they're magnetic. But they're instantaneous, and also it's like a open string, weak gravity type of thing, wormhole, where it can form light. Like I said, wherever there is weak gravity, light can easily travel. Strong gravity cannot travel. So the light gravity wormholes exist, and the light can travel easily through that speed of light. So many they form like strings. So you can have many like that, many wormholes which are strings.
Well, I'm just thinking, you know, if you have this black hole and maybe, like you say, it has a magnetic field, then now I guess it doesn't really work, because you're talking about the singularity joining up with the event horizon into a loop, yeah. Then what happens to the magnetic field in such a scenario?
No, the wormhole thing is better. I think the wormhole is a weak gravity. So the conjugate of that is just,
this is a wormhole, but it's a closed loop wormhole kind of idea. So it becomes a ring, which could, I'm just wondering, like, if you have, could that form then a magnetic field, which is
inside that,
or not even inside, but even outside of it. If you're saying there's a vortex, could be a vortex.
So the
ends of the closed loop wormhole, then that would be a. I suppose could it be a monopole, or would it have to be a dipole? I don't know. Anyway, these are just things.
The ends of the wormhole will be monopoles. Ends.
Oh, yeah. Fair enough. Yeah, I kind of have that with the. I suppose my model already deals with monopoles in a specific way because of the light beams, you know. So that's why I have that magnetic monopole. You know, gravito. No, yeah, something like that. Anyway, I'd have to go back and look at it, but the monopoles are connected to gravity, and project things from the surface of the tangent sphere to the tangent plane. But yeah, so then that would just imply that the other part of my model that's talking about these toroidal, maybe closed loop wormholes would then just relate back to string theory, you know, with the winding number where the string is wound around the torus. Maybe that could play a part in that, but really that whole thing is more sort of conjectural early days stuff, but it's still fun to talk about, you know, because it's kind of in there with the monopoles and wormholes and the gravity and all like that you're talking about often. So, okay, Rajan, we'll probably have to sign off there.
Yeah.
So I need to get some food, and it's been good chatting to you. We're going for.
We'll see you next week, and then I will send out the email.